Right, so what we have here is a situation in which an economy, small economy, depends on two interrelated commodities, steel and lumber. So what that means is that we produce steel and lumber, and each unit of steel and lumber requires some type of units of steel and lumber. So it's all kind of an ecosystem thing happening here. Thing about it takes money to make money. That's kind of what we're talking about here. So we're going to say that we want to produce X units of steel and Y units of lumber. And what we're told is that to produce 1 unit of steel, we need 0.2 units of steel and 0.4 units of lumber. And to produce a unit of lumber, we need 0.3 units of steel and 0.6 units of lumber. So we have a couple things happening here. We have steel to steel, we have steel to lumber, we have lumber to steel, and we have lumber to lumber. So it's basically a units game. So if X is a number of units of steel that are produced, so where does it go? Okay, it takes 0.2 units of steel to make steel. So that means from steel to steel, it's 0.2X. And it takes 0.2 units of steel, or 0.4 units of lumber to make steel. So lumber to steel would be 0.4X. Okay, so the 0.3 units of steel to make lumber. So for every unit of lumber I want to make, it's going to take 0.3 units of steel. So that means it's going to be 0.3 Y. And for every unit of lumber I want to make, it's going to require 0.6 units of lumber. So here's what we have. This is how much steel is used. And this is how much lumber is used. So steel used would be 0.2X plus 0.3Y. And lumber used would be 0.4X plus 0.6Y. Now, that looks unassuming right now, but we can write that as a matrix product as we learned in the last section. We know that we can write this as such right here. So that means that the information that was provided in the original problem can be formed directly into a matrix if we look at it the right way. So I'm going to call this it sometimes is called a technology matrix. And what that means is it represents what's used due to the technology. Okay, so notice how this is set up. So the 0.2 and 0.4 up here turn out to be my first column here. And my 0.3 and 0.6 here end up being my second column. Now, how can we rationalize this? Well, if I look at this as a from, and I look at this as a to, it makes sense, right? To go from steel to lumber, from steel to steel, it's 0.2. How many units are going from steel to lumber? 0.4. And so on. So columns represent making a unit of steel and making a unit of lumber. So there we have that. So now where does this go? Well, I'm going to call this matrix A, and I'm going to call this matrix X. So that means that AX is what's used in production. So that means that the quantity, so remembering that I have X to start with, that means X minus AX is left over. Now I'm going to write this in a slightly different way. I know that multiplying any matrix by the identity matrix is just going to give me the matrix again. So I'm going to write it as IX minus AX. I want them both to look like two matrices. And then kind of reversing multiplication. Remember that matrix multiplication is not commutative, so I have to make sure that I multiply X to the correct side. In this case, it's the right side. So that's I minus AX. And what this represents is leftover. Now, question. What if we want a demand matrix left over? Well, what does that mean? That means we want I minus A times X to equal D. Well, remember from the last section, we can solve for X by applying the inverse to both sides. And here is where we end up with our lovely formula. Okay, so if you have a certain amount that you need to be left over, that could be for the people who are consuming in the economy, whatever. This is your formula on how to do that right there. So that's how we got here. So hopefully that makes sense, and hopefully that gets us going and get ready to solve some really cool problems.